This is Lecture 9 Bivariate Regression. By the end of this lecture, you should be able to interpret a regression coefficient, interpret a significance test for a coefficient, interpret a constant in a regression analysis, interpret a significance test for a constant in a regression analysis, calculate an estimate from a regression equation, calculate the errors from a regression equation, interpret an R-squared and adjusted R-square, and know when to use an ordinary least squares regression to interpret the relationship between two variables. In the previous lecture, I showed you how to calculate a correlation coefficient between two variables. A correlation coefficient tells you the direction and magnitude of the relationship between two variables, but it does not distinguish between one variable being an independent variable and the other variable being the dependent variable. In addition, it does not tell us the specific impact of an independent variable on a dependent variable. Sometimes we want to know, as the independent variable changes by 1, by how much does the dependent variable change? In this lecture, I'm going to talk about ordinary least squares regression. Ordinary least squares regression tells you the specific strength of the relationship between an independent and dependent variable. It assumes that the independent variable has a linear effect on the dependent variable. In other words, it assumes that the effect of the independent variable on the dependent variable is the same across all values of the independent variable. Therefore, a change in the independent variable at small values of the independent variable and a change in the independent variable at higher values of the independent variable have the same effect on the dependent variable. Ordinary least squares regression also tells us by how much the dependent variable changes as the independent variable changes by 1. To illustrate the intuition behind calculating a regression analysis, I gathered data on the net migration of countries in 2010, the dependent variable, and the GDP per capita of those countries in 2009, the independent variable. I expected GDP per capita to have a positive effect on net migration, as in, as the GDP per capita increases, more people will migrate to the country than leave the country. I present the data in this scatter plot. When I run a regression on this data, the regression analysis creates a line that literally goes right through the middle of these observations. One way to formally represent a regression equation is to write y hat equals b hat times x plus a hat. Y hat is an estimate of the dependent variable. B hat is the coefficient slope or beta. X is the independent variable, and a hat is the constant y-intercept or alpha. Now imagine I tried to draw a line through the middle of these observations myself and tried to estimate the regression equation. The y-intercept a hat would be the value of y when the line passes through the y-axis. Next, the slope b hat is simply the change in y over the change in x. B hat is very important in the regression equation because it tells us whether the independent variable has a positive, negative, or neutral effect on the dependent variable. If the coefficient has a positive sign and is statistically different from 0, then the independent variable has a positive effect on the dependent variable. As the independent variable increases, the dependent variable increases. If the coefficient has a negative sign and is statistically different from 0, then the independent variable has a negative effect on the dependent variable. As the independent variable increases, the dependent variable decreases. If the coefficient is not statistically different from 0, then there is no evidence that the independent variable has an effect on the dependent variable. As the independent variable increases, the dependent variable stays the same. Last, the coefficient also tells us the specific effect that the independent variable has on the dependent variable. For example, if b hat equals positive 1.5, as the independent variable increases by 1, the dependent variable increases by 1.5. If, on the other hand, b hat equals negative 1.5, as the independent variable increases by 1, the dependent variable decreases by 1.5. Now that I have shown you the intuition behind a regression equation, I'm going to briefly show you how b hat and a hat are formally calculated. B hat is the sum of each x observation minus the mean of x times each y observation minus the mean of y, and that value divided by the sum of each x observation minus the mean of x squared. All this is really trying to calculate is whether each x deviates from its mean in a similar manner to its corresponding y deviating from its mean. This is similar to the correlation coefficient calculation. A hat is simply the mean of y minus b hat times the mean of x. Fortunately for you, I'm not going to ask you to calculate b hat and a hat in this course. I will cover that material in Political Science 398. Instead, I'm going to show you how to run and interpret a regression analysis in SPSS. For this course, we will let SPSS calculate our regression equation for us. The first step in running a regression analysis in SPSS is writing null and alternative hypotheses. The null hypothesis always says that the coefficient b hat is equal to 0. This means that you do not expect the independent variable to have an effect on the dependent variable. The alternative hypothesis always has a direction. If it either says that the coefficient b hat is positive and greater than 0, or negative and less than 0. If you expect your independent variable to have a positive effect on the dependent variable, then your alternative hypothesis should be b hat is greater than 0. If you expect your independent variable to have a negative effect on your dependent variable, then your alternative hypothesis should be b hat is less than 0. Now, going back to the example from the beginning of the lecture, I expect GDP per capita to have a positive effect on net migration in a country. So my null hypothesis would be that b hat equals 0, and my alternative hypothesis would be b hat is greater than 0 for a positive effect. After you write your hypotheses, you run your analysis in SPSS. In SPSS, you click Analyze Regression Linear. You put the dependent variable in the dependent box, and you put the independent variable in the independent box. This is what a regression output from SPSS looks like. The third step is interpreting these results. The first step in interpretation is writing out your regression equation. The equation is the dependent variable hat equals b hat times the independent variable plus a hat. We know that our dependent variable is net migration, and our independent variable is GDP per capita. So we can just insert that information here. Now we need to find b hat. All the information you need for b hat is located in the bottom row of this last table. The b hat is located in the B column, 19.045. All the information you need for a hat is located in the top row of this last table. A hat is located in the B column. Yes, I know this is confusing. Negative 182,752.154. So our equation would be net migration hat equals 19.045 times GDP per capita minus 182,752.154. Note that I subtracted a hat because a hat is a negative number. The next step is determining whether the coefficient, or b hat, is different from 0. Now, most of the time, b hat will not actually be 0. However, just because b hat is not 0 does not mean that it's not statistically different from 0. If b hat is not statistically different from 0, then there is no evidence that the independent variable influences the dependent variable. If b hat is statistically different from 0, the independent variable has an effect on the dependent variable. It is a positive effect if b hat has a positive sign, and a negative effect if b hat has a negative sign. Once again, if it is positive, as the independent variable increases, the dependent variable increases. And if it is negative, as the independent variable increases, the dependent variable decreases. I am not going to teach you how to calculate whether a coefficient b hat is statistically different from 0. Once again, I will cover that in Paul's 398. But I will tell you the intuition behind the calculation. We use a t-test to determine whether a coefficient b hat is different from 0. This is similar to when we use the t-test for difference of means test. We divide the coefficient b hat by the standard error of the coefficient. The standard error of the coefficient takes into account how well the regression model predicts real-world outcomes. If it predicts the true dependent variable values well, the standard error is small. If it predicts poorly, then the standard error is larger. Now, recall that in a t-test, you want to calculate a t-statistic. You want to calculate a large t-statistic because it means that the t-statistic is greater or less than the t-value you get from the t-table in your textbook, and that indicates a significant relationship. The way to get a larger t-statistic in this equation is to get a model that generates good estimates, which leads to smaller errors, which leads to a smaller denominator, which leads to a larger t-statistic. Now that I have shown you the intuition behind a significance test for a coefficient b hat, I will show you how to determine whether a coefficient is significant based on SPSS output. First thing you need to do is determine whether the sign of the coefficient b hat has the correct sign. If your alternative hypothesis said that b hat should be greater than 0, then the coefficient should have a positive sign. If your alternative hypothesis said that b hat should be less than 0, then the coefficient should have a negative sign. If it has the right sign, then you move on to the directions in the next couple of slides. If it does not, then you move on to step 5b, which I will discuss later. As you can see from our regression output, we expected GDP per capita to have a positive effect on net migration. The sign of b hat is positive, which is what we expected. So we move on to the next step. So if your b hat has the correct sign, the first thing you should do is look at the sig value for your coefficient for your b hat. The last cell in the bottom row of the last table here gives you a sig value for your coefficient b hat. To determine if the coefficient b hat is significantly different from 0, follow these steps. Start with this first criterion here. If the sig value is less than 0.002, then the coefficient is significant at the 0.001 level. If the sig value does not meet this criterion, move on. If the sig value is less than 0.02, then the coefficient is significant at the 0.01 level. If the sig value does not meet this criterion, move on. If the sig value is less than 0.10, then the coefficient is significant at the 0.05 level. If the sig value does not meet this criterion, move on. If the sig value is greater than 0.10, the coefficient is insignificant and indistinguishable from 0. Now, you may be wondering why these values here are not the same as these values here. These values are simply these values divided by 2. I did that because in SPSS, it does a two-tailed test of significance for a coefficient b hat, but we only want a one-tailed test, like in this picture here. We expect our t-value to be large and positively different from 0. A two-tailed test assumes you have no idea of how your independent variable should affect your dependent variable. It could be positively different from 0 or negatively different from 0. This type of test assumes the percentages for the test are divided into 2 within these two tails. So for 5% confidence, for example, we would have 2.5% in the lower tail and 2.5% in the upper tail for a total of 5%. But of course, if we only want 5% in one tail, we have to divide the p-value or the sig value by 2, because that turns the significance test from a two-tailed significance test into a one-tailed significance test. Now, if your coefficient is significant, you can interpret it, which I discuss in step 5a. But if the coefficient is insignificant, you move on to step 5b. Going back to our example, our coefficient is significant at the 0.001 level, since 0.000 is less than 0.002. If you have a significant coefficient, you should write the following. I reject the null hypothesis that the coefficient is equal to 0. The results suggest that there is a significant relationship between the independent and dependent variables. You should also note if the relationship is positive or negative. If the coefficient b hat is positive, there's a positive relationship between the independent and dependent variables. As the independent variable increases, the dependent variable increases. If the coefficient b hat is negative, there's a negative relationship between the independent and dependent variables. As the independent variable increases, the dependent variable decreases. You also note the level of significance, 0.001, 0.01, and 0.05. Next, you write, as the independent variable increases by 1 unit, the dependent variable increases or decreases by the value of the coefficient b hat. The dependent variable increases if the coefficient is positive and decreases if the coefficient is negative. So going back to our example, we would write, I reject the null hypothesis that the coefficient is equal to 0. The results suggest that there is a significant relationship between the independent and dependent variables. There is a positive relationship between GDP per capita and net migration. This relationship is significant at the 0.001 level. As GDP per capita increases by $1, net migration increases by about 19 people. Now on to step 5b. Imagine the coefficient is insignificant because the coefficient had the wrong sign or the sig value is greater than 0.10. Then you say that I fail to reject the null hypothesis that the coefficient is different from 0. The results do not suggest that there is a statistical relationship between your independent and dependent variables. You cannot make any conclusions and you do not have support for your argument. Next, you have to determine if the intercept a hat is different from 0. The sig value in SPSS for a hat is at the end of the row here, the constant row. Start with this first criterion here. If the sig value is less than 0.001, then the intercept is significant at the 0.001 level. If the sig value does not meet this criterion, move on. If the sig value is less than 0.01, then the intercept is significant at the 0.01 level. If the sig value does not meet this criteria, move on. If the sig value is less than 0.05, then the intercept is significant at the 0.05 level. If the sig value does not meet this criteria, move on. If the sig value is greater than 0.05, the intercept is insignificant and indistinguishable from 0. Note that I did not divide the sig values by 2 because, unlike a coefficient, we do not have an expectation of whether an intercept or a hat should be greater or less than 0, so we used a two-tailed test. Now back to our example. Our a hat is significant at the 0.01 level because 0.0002 is less than 0.01, but not less than 0.001. Next, you interpret the intercept a hat. Sometimes it makes sense to interpret it, and sometimes it does not. A hat tells us what the value of the dependent variable would be if the independent variable had a value of 0. So in this case, when GDP per capita is 0, net migration is predicted to be negative 182,752. This is unrealistic because no countries in the world have a GDP per capita of $0. Now I'm going to show you how to calculate a point estimate from a regression equation. You can calculate an estimate for each observation. You only do this if the coefficient is significant. So we have this equation here. Net migration hat equals 19.045 times GDP per capita minus 182,752.154. We insert the value of the independent variable here. So let's say in observation 1, GDP per capita was 10,000. We would calculate net migration hat equals 19.045 times 10,000 minus 182,752.154, which equals 7697.846. An estimate from a regression equation gives us an estimate for a specific observation. Sometimes we want to know how far our estimates deviate from the actual values of the observations. This is known as the estimate errors. To calculate the estimate error, you take the actual value of the dependent variable for a specific observation and subtract the estimate from it. So in our previous example, the estimated net migration was 7697.846. Imagine the actual net migration for that observation was 112,000. So we would calculate 112,000 minus 7697.846, which equals 104,302.154, our error. The last topic I'm going to cover in this class is how to interpret an R-square from a regression analysis in SPSS. I cover how to calculate an R-square in Paul's 398. An R-square tells us the extent to which the variation in our independent variable estimates the variation in our dependent variable. In other words, how well does the independent variable predict the dependent variable? In the SPSS output, you can find the value of the R-square in the model summary box here. An R-square ranges from 0 to 1. Values close to 1 indicate that the independent variable estimates the dependent variable well. Values close to 0 indicate the independent variable estimates the dependent variable poorly. In our example, the R-squared was 0.151. You move the decimal place over twice and make this value a percentage. Then you state that variations in the independent variable explain the R-square percentage variation in the dependent variable, or in this case, Variation in the GDP per capita of a country explains 15.1% of the variation in net migration in that country. Last, the adjusted R-square simply modifies the R-squared to take into account the number of observations and the number of independent variables into account. You calculate an adjusted R-square by taking 1 minus R-square times the number of observations minus 1 divided by the number of observations minus the number of independent variables minus 1. What this equation does is make an R-square smaller if there are a small number of observations or too many independent variables. Theoretically, if you have too few observations in relation to how many variables you have, you may not have adequate information to predict your dependent variable. So the adjusted R-square punishes you for not having more observations. In the SPSS output, the adjusted R-square is located in the model summary box here. In our example, it was 0.147. Like the R-square, you move the decimal place over twice and make it a percentage. Then you state, after taking into account the sample size and the number of observations, variation in the independent variable explains the adjusted R-square percentage variation in the dependent variable. Or in our example, after taking into account the sample size and number of observations, variation in the GDP per capita of a country explains 14.7% of the variation in the net migration in that country.